Hello. All right. Welcome to chapter 2. We are in the second lesson now on astronomy. This lesson is going to be cut into two because there's quite a bit of material. First off, astronomy. It's the science of objects that originate outside of Earth's atmosphere. All right. So we reside around our local star called the Sun, which is one of an estimated 100 billion stars in the Milky Way galaxy. So you can see, and the Milky Way is only one of an estimated 100 billion galaxies in the universe. Now that is really hard to wrap your head around, right? That is bizarre. So our sun is one of 100 billion stars in the Milky Way, but then there's another like 100 billion galaxies, like crazy. Anyways, the universe is estimated to be about 46 billion light years across and getting bigger every second. Huge. All right, so we're just going to focus in on the sun, which is a star closest to us, and the electromagnetic radiation that's coming from the sun, and also some of the other stars around in our Milky Way. So the sun, our star closest to us, just like other stars, it produces energy in its core, right inside the center there. And this energy is created through a nuclear reaction called nuclear fusion. Right, where you have two hydrogen atoms, they combine to form hydrogen and also a neutron. Now we're going to look at more at nuclear reactions in Unit 4, but for now you just need to know that this nuclear fusion reaction is what gives the sun the ability to produce all of this energy, and this energy is in the form of electromagnetic radiation. So how did the sun form anyway? So one of the things you do need to know is about how different types of stars form. And we're going to look at the different types of stars. So first off, we're going to look at the sun because it is the closest star to us. How do all stars form? Well, they all just form from a big cloud of hydrogen gas and dust. And that's what a nebula is. You've probably heard that term before, a nebula. So there's some really gorgeous pictures of nebulas if you go onto the internet and search nebula. There's some examples of some different nebulas. So these are before stars even exist, huge clouds, hydrogen gas, and dust. These gases, they begin to collide, all right, collapse, come together, heat up, and they create their own gravitational attraction, which is causing this energy to start heating up. When the internal core temperature becomes, 10 million degrees, that's when you start to get the nuclear fusion and a core beginning. And with this nuclear fusion, that is when EMR and energy is produced. And this production of energy helps prevent the stars from collapsing. Okay, so when you're asked why do stars shine, right? All kids like to ask that question. Why is the star shining? It's because of nuclear fusion. Very exciting answer. All right, so how did the sun form? All right, so I just realized I have the same slide. We've already gone over this material. But basically, it's the reminder of the nuclear reaction that's inside the sun, which is what's producing the electromagnetic radiation that's giving off all that energy from the sun or stars. So temperature of stars. Stars appears to be different colors at night. So you can even see from this picture, there's red stars, some blue stars, there's white stars. And the hottest stars have their peak in the continuous spectrum with the ultraviolet region. So our eyes see these stars as bluish white. Okay. Our sun appears yellow. It's cooler than the hottest stars. So our sun's around here. And the hottest stars, you're getting hotter as you go towards the violet or white bluish end. So you might see white bluish end here. These are the hottest. Has the most amount of energy. And remember, if you look on your data booklet, as you move to the right on your EMR spectrum, right? Remember that? The energy increases, right? So we get closer to the gamma rays. And it's the same with this idea of looking at figuring out the star temperature. So the hotter or higher energy stars are the ones that are going to look at the colors at this end of the spectrum. So if you're starting to look blue or white, you're higher than a yellow or orange sun or star. All right, the evolution of stars. All stars begin in regions that are rich in hydrogen and dust. Remember, we call these, do you remember what we call them? Nebula. Yeah. All right. So eventually hydrogen runs out and the star's fusion stops. It can't make any more energy. And so our star is considered a low mass star. So when we're talking about the sun, we're talking about a low mass star. There's intermediate mass stars and high mass stars. When you run out of mass, nuclear fusion stops, and that is the end of the star's life cycle. So we'll take a look and see what that end, middle, and beginning looks like for different stars. And these reactions tend to occur more quickly, more rapidly with stars with larger masses. So first off, we'll look at our sun because it's closest to us and most interesting to us and affects us the most. So it's a low mass star. And they spent their main sequence lives using fusing hydrogen into helium in their core, okay? So the main part of the life there, this fusion reaction is occurring. So a low mass star is considered a star if it has 1.4 times or less the mass of our sun right now. So here's its life cycle. It starts off as a nebula, basically gas and dust, then becomes a low mass star. So this is where our sun is right now. Okay. And then it becomes a red giant, and then an expanding shell of gas, and then it ends in a white dwarf. Now, you do not need to know what each of these different steps looks like. You just need to know the steps along the way from nebula or gas to white dwarf for a low mass star. Okay, so this is like a straight memorization deal. There's a great video. I strongly suggest watching it. I'll give you a little bit more information on those low mass stars' life cycle. Then we have intermediate mass stars. So these have about the mass of Earth times 1.4 to 8 times the mass of our sun. Sorry, not Earth, sun. So bigger than our sun, obviously. Again, they still start as a nebula. And then you have your intermediate mass star. And this is where your star is doing its fusion reaction. And then it turns into a supergiant star, a supernova, and then a neutron star. And then high mass stars. So these have a mass 8 times greater than the mass of our sun. Again, they start out as a nebula. Then they become the high mass star. Supergiant, the star collapses, and this is where we get black holes. Okay, so you can read more about this in the textbook as well, especially if you're interested in all these different stages. And there's also, oh, I thought I put a video in here. Maybe not. Okay. Oh, no video on that one. Okay. Here we go. Okay, so we have a little bit about the black holes, which is the last stage in the high mass star's life cycle. And this is an area with a super, super strong gravitational field that matter nor electromagnetic energy can actually escape. So the electromagnetic waves can't even get out of this gravitational field. So when you have a large star and it runs out of fuel, so remember its fuel is hydrogen, so it can't do the fusion reaction anymore. That pressure, it pushes inwards and forces the star to get smaller and smaller and smaller. So it's really small. It's smaller than an atom by the end, right? And what is really interesting and hard for me to even comprehend is that gravity, as you get smaller, as you force that object to get smaller and smaller and smaller, squish it, the force of gravity gets bigger and bigger and bigger. So if you squish a star into the size of an atom, its power of gravity is unbelievably large. And so light can't even escape from that area. Anything that gets close gets pulled right into that black hole. Now, how do they find black holes? Well, there's gases that can form around the black hole, and they can heat up and they can give off X-rays. So a lot of times scientists are looking for X-rays from a dark area of space. And there's a lot more to it, but I would suggest doing a little extra reading if you're interested on black holes. So, diploma question. So this is the kind of question you're going to get for diploma or from my unit tests. And it's more about what are the stages in these different stars. So in this question, some of the stages in the evolution of a small star, so we're talking like our sun, fusion begins, a white dwarf forms, and a red giant. So we have a low mass star such as the sun, begins as a collection of dust and gas, nebula. As the star evolves, the sequence in which the stages numbered above occur is. Okay, let's pause here. I know you got the answer, but let's go back to see our small sun. And by small sun, I meant low mass star, like our sun. So what do we got? We've got it starting as a nebula, gas and dust, goes to low mass star, a red giant, and then a white dwarf. So white dwarf is what it ends in. Okay, not a black hole like the high mass star. So we're looking at white dwarf. So let's go back to our question. So white dwarf, there you are. That's what our sun, our small star is going to end in. Fusion begins. Fusion begins when it turns into a star, into the low mass star. So that's the first step after the nebula. And then the red giant is the step in the middle there. So it's mostly the parts of the life cycle of the star that you need to know in the order that they would occur. All right, let's take a second to read this question. Okay, it's handy. We just looked at what a low mass star's evolution is. So again, everything starts with that nebula of gas and cloud and dust. Then we have two stars happening here. So we have a low mass star, right, like our sun, becoming a red giant. And then we have a high mass star becoming a supergiant. Basically, what are each of these ending in? It says, which of the following rows identified the most likely end products of each of these two star sequences above? Well, we just saw that the low mass star turns into a white dwarf. And a high mass star, and I hope you remember this one, the high mass star is always what turns into a black hole, because you need lots of mass to form the black hole. So 2 will be a black hole, 1 will be the white dwarf, and that is why your answer is A. All right, moving on. Now we're going to look at some of the different properties of electromagnetic radiation. And these are all properties that are not only true for light that we see, but for all the different types of electromagnetic radiation that we don't see with our eyes. Okay, so keep that in mind when you're thinking about these different properties. So the first one that you need to know is about refraction, and this is the bending of light. Basically, as light enters, or EMR enters a different medium, say you're going from air into water, that light is going to bend. Okay. Also need to know the term reflection. And this is when light bounces, basically, or is reflected off of a surface, like a mirror is a good example. For reflecting, your incoming ray is always coming in. Here's the angle. We measure this angle to what's called the normal line here, which is just a line that's perpendicular to the surface we're coming in on, like at a right angle degree, right? So the incoming light angle here, that angle is going to be the same as the reflected light angle here. Okay. That is the rule with reflection. The incoming light has to be equal to the outgoing light, reflected light ray. Okay. Good video on reflection versus refraction, making sure that you understand the difference. Also, how refracted light speeds up or whether it slows down when it hits a dense medium like glass. Hopefully you think, it's probably going to slow down when it goes through glass, and you would be right. So we have the opposite here, actually. I have a ray of light coming from water into the air. Once that ray of light hits the air, it can speed up a lot, and it's going to, and you can see it speeds up here. And how can you tell it speeds up? Well, if it was just going straight through and not doing any kind of speeding up or slowing down, it would just look like that. Okay, we go straight through. That's what that dotted line represents. But because it's speeded up, it actually has moved away from what we call the normal line. Remember the normal line? It's the perpendicular line to the surface. So it's sped up a bit. So it's moved away from the normal line because it's sped up in air. All right, a couple other properties you need to know about. Polarization. This is when electromagnetic radiation is confined to vibrate in only one direction. All right, so you can put this polarization gradient on, and you know how electromagnetic radiation, you can see from this image here, has waves in all different kinds of directions, perpendicular to and all over the place. If you put a grating like this here, it only allows waves that can fit through the grating in one particular direction, right? So you're only going to get one of the waves coming through. And this reduces glare. These are great. This is where you find these in polarized sunglasses. And there's a video on the next slide to make sure you get an idea of what polarization looks like. Basically, you're only allowing one type of wave in one direction through. Okay, so you have a grating. Then there's the term diffraction, and this is the bending of electromagnetic wave as it passes through an obstacle. Okay, so and spreading out too, so these waves can get through and out. You're not going to see this one very much. It's not as common. Alrighty, moving on to, I gotta pause that. So this section now starts getting into space probes, telescopes, looking at EMR that's coming from space and ways that we can collect it and what we can figure out and why would we even want to collect those. So we have all probably looked through a telescope to see visible light and looked at like the moon or a star through a telescope, but you can only get a limited amount of information with visible light. So we actually will collect, and I say we, astronomers, will collect other types of electromagnetic radiation from space, and that can help us determine other things like what is that star made up of, its temperature, how fast and in which direction it's moving. So some of the things, you know what, I think I moved this slide later on in the lesson, so I'm going to hit it later in a second. I know, we're going to deal with it here. I forgot. Okay, so space probes and telescopes. Telescopes like the Hubble, which we're going to talk about in a bit. There's other satellites and space probes that are out there too that can detect a wide range of electromagnetic radiation, including infrared, UV, visible light, microwaves, and radio waves. And so some of the benefits to using such expensive technology, because it's definitely not cheap to put things up and in space, in orbit, but as we mentioned before, it lets us figure out the temperature and chemical composition of some of the different planets and gases that are out in space. We can find supernovas, pulsars, neutron stars, black holes, maybe even what planets are similar to Earth and which might be habitable, right? And then it also allows us to understand the history of Earth itself a bit better, and our sun too, as we saw with the different star cycles. Now, some of these technologies are very expensive, and also because of that expense, only certain countries are able to actually set up and put these space probes and telescopes into space. Also, there's materials that might be toxic during takeoff. Also, just recently in the news, we've seen pieces falling off or coming out of orbit, and not knowing exactly where those are going to land can be a problem as well. So we talked about reflection and refraction, and why we bring those up is because those concepts and principles are used in telescopes. So this is a refracting telescope. Remember, refracting is when light bends because it enters a different medium. And in this case, the medium is a lens, right? So this is a glass lens, or it might be made out of other materials. It's a different medium, and it makes the incoming light, or EMR, actually bend, and to bring it towards a one smaller exit location. So a telescope that magnifies an image by using lenses to bend light. Also, if you have a larger opening, you can get better resolution. All right, but we don't really need to go into much more detail. All you need to know about refracting telescopes is that they use lenses, and they work on the principle of bending light. Okay, that's the key piece that you need to know. There's so many details about these, but you don't need to go crazy. Again, we also have reflecting telescopes. So these are using a concave mirror. So a concave means it's bent like this. So a mirror to reflect the light into the eye. And that's the key piece that you really need to know. There's mirrors involved because we're dealing with reflection, okay, and reflecting rays. Some of these big telescopes here, there's an example of a reflecting telescope on page 443. There's a Canadian, France, Hawaii telescope, which you can read about more in your textbook. And a little bit more about that same telescope, and some more things you can read about from your textbook if you want. So reflecting telescopes, there's a really large one. It's very popular, the Hubble Space Telescope. This is a reflecting telescope, and it's collecting infrared, UV, and visible light. So all those that whole range there, and any other EMR emitted from planets that it can get. So planets, comets, asteroids, anything that might be coming near it or in its detecting range. And why is this Hubble telescope? So this thing is obviously not on Earth, right? It's up in space. They're launched high into the sky so that Earth's atmosphere doesn't absorb any EMR, right? So they got to get above the atmosphere to get really good pictures. This video on the Hubble Space Telescope, really good video. I suggest watching that one. So again, why do we put the Hubble up high? Because you want to get it up there so that it can get the different light waves, the different EMR that's getting blocked by our atmosphere. And this image in your textbook on page 439 shows you that visible infrared and some UV light from the sun will get to Earth's surface. So let's see. There's the visible light. Infrared and UV. So you can see some of the arrows representing the rays of that electromagnetic radiation do make it all the way to Earth. But there's quite a big range there that does not get to Earth. So X-rays are blocked off, gamma rays, thank goodness, ultraviolet, most of them are as well. So long wave, what about long wave radio? It's absorbed by Earth's atmosphere as well. So here's the long wave radio areas. But shortwave radio, you may have heard, or like my grandpa had a shortwave radio to communicate with people all over the world. And shortwave radio can make it to Earth and go around through the atmosphere. X-rays and gamma rays are absorbed by Earth's atmosphere, which is good. Otherwise, there'd be a lot of damage because they are pretty high energy. And then most UV is absorbed by the atmosphere. Except remember, we've got some of those holes in the ozone. Remember those? And that's a bit of a problem. So more UV light is getting through, and we don't want that. So this is just another picture emphasizing the two types of main types of telescopes that you'll find actually on Earth. So you'll see these radio telescopes, because remember, we do see a lot of the shortwave radios coming from outer space, from the from our universe, as radio waves, so we can catch those on Earth, and also the visible light, ultraviolet light, and some UV are coming to Earth. So we can have the optical window, it's called, and the radio window. So we can have telescopes that capture those types of radiation on Earth. And this is an example of a radio telescope. You may have watched some movies, if I could remember the name of them right now. But this disc has been used actually in quite a few films. It's so funky and alien looking like, but it's basically just a big giant dish, a telescope to collect the radio waves. And if you remember about radio waves, their wavelengths are huge. They're really big, and that's why the radio waves have to be so big. They're very long wavelengths. Yeah, so you've probably seen these as well. I think those are in some movies I used to try and find aliens. But yeah, so these really giant dishes, they are collecting radio waves. And that's the end of the part